Okay, so good afternoon. So I hope my slide is visible. We are discussing about the parametric methods of Bayesian inference mechanism, and particularly their Bayesian classification. And there we have seen that actually parametric methods are used to estimate the probability density functions of different components of Bayesian inference, like likelihood, then the prior, and also the marginal probability to compute the posterior. But for estimating the parameter itself, we use two types of approaches, and we discussed both the approaches in the last class. One was the maximum likelihood uh, estimation approach, where we are maximizing the probability of data given a parameter. So that is say the likelihood of a parameter given data. So it is defined in this manner. And on the other hand, the other approach, uh, which is similar to the Bayesian inference, that is computing the posterior probability of the parameter given the data. So the here it is in the same way you should no, compute these probability density functions we discussed, but just to summarize the points once again, you can see that computing posterior again involves similar to the likelihood computations, again involves probability of data given the parameter. Then you need to have a prior distribution of the parameter space. Now, which is usually obtained by different mechanism. So there is so with that, from the data, it is difficult to get a prior distribution. So you are not doing that. And similarly, uh, the the denominator part, that means the marginal probability, that also a requires a computation of data. Now there, once again, if you have the prior distribution, if you have the distribution of the data given the parameter, or we may call likelihood distribution given the parameter, then with this, no, you can also get the marginal probability, but the computation here is expensive, right? So that is what I just mentioned, that mostly priors are assumed. You may estimate by other means, but not from data directly. Then it is difficult to compute the denominator, as you have seen, that you need to do that kind of integration over the space. And finally, the decision on the parameter, that means what should be the estimated parameter, there are two ways of taking this decision. One is like the classification approach, map approach of deciding about a class by maximizing the posterior for class posterior. Here also you can consider that parameter set, which is maximizing the posterior distributions if it is a narrow distributions. You know that integrations of posterior would give 1. Given the data, integration would give 1. But if it is narrow, means it's within a narrow interval only you get the positive, we get the positive non-zero values. Otherwise, outside it is almost 0. So in that case, you can consider this map approach. Otherwise, the optimal approach should be that you take the expectation of parameter value, expectation of the parameters values with this distribution, which is given by this. So which we call that Bayesian, this is true to the Bayesian inference mechanism. So we call it, say, Bayesian estimation. So for your example, I think someone's microphone is on, please mute it. So I would give an example once again using this Bayesian estimation technique for the normal distributions. Like you have seen that maximum likelihood estimates of parameters for the normal distributions like mean and standard deviations. Mean is simply the average sample mean. I mean, mu is sample mean. That is the estimation which was unbiased. But whereas the standard deviation or the variance, you have to have little modification on the sample variance. We have seen that, no? That you take the sum of square of deviations from the sample mean, but then you, instead of dividing by the total number of samples, you just divide by one less. That means if the number of sample is n, you divide it by n minus 1. So that would give you the unbiased estimate of the parameters. When these are all maximum likelihood estimate based approach. Let us see that how Bayesian approach gives you what kind of results you get. Now, as I mentioned that in this case, you consider a prior distribution of the parameter set. So let us consider that you have the distribution of mean only, of course. Now, let us consider only mean. Huh? So let us not bother about the sigma value variance. So mean also follows a Gaussian distribution. It's a Gaussian prior, where that means theta includes the mu. I'm talking rather no, let me call it this parameter as a mu, which is representing the expectation of the Gaussian distribution. So mu also follows a Gaussian distributions as a prior. So you know that much of the importance is given on mu naught. So most of the times you are expecting this parameter should be mu naught, our maximum probability around mu naught. And also there is a variance of that means sigma naught square, which shows that how how reliable or how robust is that kind of thing. So but no, so it should have an weight. So if I follow the Bayesian estimation approach, as you have already seen that this is what is the data given that parameter. I'm assuming that sigma is fixed. So given the sigma, so for the value of mu and sigma, given mu and sigma, this is the likelihood value. You can see that it is multiplication of all individual, all individual probabilities following the normal distributions. That is what you are getting here. And so this is your likelihood of the data given the parameter. Then you have to multiply with prior, and which is expressed in this form because it's a Gaussian prior. But you need to compute the marginal probability. That is a bit expensive, but I'm not showing you all the steps there. So finally, if you see the result I'll be telling you that if you consider the estimation of the value mu, I have written theta. Actually, we are estimating here mu. That means the mean of the distributions or expectation of the distribution. So there you can see it is not exactly the sample mean. It is basically it is weighted value of this mu is actually sample mean here. So weighted value of the sample mean and also the prior the expectation of the prior distribution mu naught. So there is a relative weightage. You can add those weights. You can see they are 1. So this is the interesting result that you get. So this is one kind of example where Bayesian estimate will give you a different value, different result than maximum likelihood estimation. But the complexities, as I mentioned, the prior, etc., those are the complexities. Now, if your prior is uniform, then it is the same as maximum likelihood estimate based approach. Now, if I say the classification, so how do you do the Bayesian classification using parametric methods? Now you have understood that actually you have computed the probability density functions given. You can have the probabilities or probability density functions given the parameters. So you can compute the posterior for all classes in the same way. So every component of the posterior computations are computed. Like, of course, probability of class probability or prior class probability could be estimated in the previous way as empirically how many times, what is the fraction of times a sample occurs in a class. So it would be like this. No, you can ignore also the denominator and only the numerator you can consider for class assignment. So if you consider the discriminant function based approach where every class has a discriminant function and maximum value of the discriminant function will provide you the class assignment. So there, this could be a discriminant function, or you can take the log of this value to make it more additive. So this could be also another form of discriminant functions. So these are certain things, and if you assume that they are Gaussian, then these discriminant functions, you can see that it becomes a quadratic discriminant functions. The GIX is a quadratic discriminant functions, but if I assume that all sigmas are equal, that means all class variances are equal, likelihood in the likelihood distributions depending upon class. So variances in all likelihood distributions are equal, then we can see that would be also linear. So this is what you should do. And the first term can be dropped because it is constant, and PCI is the same for, if the PCI is the same for all classes, the last term can, and as I mentioned, if the variances are same for all classes, then it becomes actually the nearest neighbor classification. So you see that no, many of the simple classifiers, they have the Bayesian interpretations in this fashion. So they are special cases of Bayesian classifications with these assumptions, right? So I should also mention that no, discriminant function-based approach there exists purely without no having any kind of probabilistic interpretations. We'll discuss in subsequent classes. Now, this discussion so far, whatever we have made, mostly we made with respect to univariate representation of the random variables. But if you have your random variable is multi-dimensional, or rather I should say multi-dimensional, in a multi-dimensional space, we call it multivariate in the sense that actually the sample, input sample has different attributes, and each attribute is a variable, and it's a multi-dimensional. So we call it multivariate representation. Suppose the dimension is D here, and you know that then it's an element of the real space, D-dimensional real space, which is represented here, and you have the n data points. So you can represent it by a data matrix. This data, you can represent it in the form of matrix, where each row or each column will represent a sample. So depending upon your representation, row-wise or column-wise representation of samples. So here, what I could see that it is row-wise representation. You could say that in this representation, it is important to know that what conventions you are following. So each row is a sample. So if there are n instances, you will have n rows. So the matrix dimension, as you see, that it should be n number of rows and d number of columns, so which means n cross d. And this is called data matrix, and your input can be represented in the form of a data matrix itself. So this is the thing. So each row is a data sample, and for this multivariate representation, so your random variable is a multidimensional random variable, and let us consider the mean of the all rows. Now, if the mean of all rows will give you a mean vector, right? So I hope you have understood by taking the basically mean of all values in single columns, that will give mu1 similarly. So mean of all rows means that. Mean of all rows, I said, from the vectorial point of view, effectively each field can be obtained from that vector by taking the mean of each column. So if you take the covariance matrix of the data matrix, then no, we consider the covariance matrix should be represented as sigma ij. Can anyone tell me that no, how covariance matrix could be computed given this representation, say x and mu? So you see, this is a data matrix x that is given to you, and mean vector is mu. So how covariance matrix can be represented? Can anyone tell? how covariance for the single dimension is represented. Suppose you have a random variable x, and its expectation is mu. So how covariance is expressed in that case? Basically, covariance would be the variance. So if I say covariance, covariance means there will be two random variables. Say one is x, as say mu x. Let me write it as mu x. Another random variable is y, and which is having the mean is mu y. So how do you represent covariance of x and y?
Sir, expectation of xy minus mu x mu y.
Good. That is very good. What is the basic definition? Can you tell me? That you have said after no simplification of an expression.
Sir, expectation of x minus mu x into y minus mu y.
Very good. So similarly, you can represent the covariance of this data matrix. So each column is like a covariate here. So which means if I take any particular ith column, uh, sorry, it's not. Yeah, each column, because each column is representing a dimension. If I take ith column and say jth column, okay, some column jth column. So let us say, so this x is representing, this variable is represented by ith column, and y is represented by say jth column. So you get the covariance of these two columns, which means this will have the, say here it is mu I, its mean is mu I for this one, and this one will have mu j, isn't it? Okay, is it clear? So now what should be the
Yes, sir.
covariance in that case? Yeah. So x minus, as you have said, x minus mu y into y minus mu j, expectation of that, or you can write expectation of the product of these individual values. That means average of these values minus mu x into mu y. That would give you sigma ij, as well as that would give you sigma ji, because this is symmetric. Now this can be also represented in a simple, in a very compact form, in a matrix, which is a bit difficult to understand if you, but no, if you extend, if you are very familiar with matrix definitions, you can get it. So in fact, this is how we write it when we write in this form, right, in the matrix form. This is what exactly what I mentioned. Huh? Okay, so covariance matrix also includes variance, right? So which are the variances? That means variance means within the random variable. What is the variances of a random variable for each column representing a random variable for that attributes? So what are the variances in covariance matrix? Where do they occur?
Sir, diagonal elements.
Right. So it's in the diagonal elements. So is there any questions on this part? This definition is very important. You should understand. It is already there in your basic linear algebra, and also particularly in probability and statistics, where you have gone through these things. But no, please note these definitions. Now there is also another matrix which is often used instead of covariance. We can use correlation matrix. So you can see that this is the definition of correlation. This is the definition of a correlation of ith and jth random variable is represented by its column in my definition. Okay, so so you can see that if I normalize the covariance by the corresponding product of their standard deviations, uh, it should be sigma ij. No, sigma ij is already, I am saying it is covariance. So actually it should be root over sigma I and root over sigma j. Sigma I is the variance. So they are standard, is a product of standard deviations. Okay, so please try to make a little more I should say that it should be actually root should be there because they are actually product of standard term. Okay, so some correlation matrix is also used in some analysis. Anyway, so these are certain definitions. I'm just again going for the uh, analysis. That means how do you compute the corresponding probability density functions or the parametric estimations, because using these entities, you define a probability density function in multidimensional space. So what you need to estimate, so your parameters, these are your parameters. So the elements of covariance matrix and elements of mean vector, they are your parameters now. So you have many parameters when you are going for multidimensional matrix, because your probability density functions are defined with respect to these parameters. Say this is the example of definition of multivariate normal distribution. So you can see that for a multidimensional random variable, you have this. I have already defined what is mu. Mu is the mean vector, and what is sigma here? Sigma is the covariance matrix for a random variable. And then they follow this distribution, normal distribution. So you can see as a special case when it is univariate, then actually it will be the same as what you see the normal distribution or Gaussian distribution for a random variable. Now, parameter estimation means, in this case, what are you going to estimate? And when you are going to compute this probability of a particular instance of a particular any probability of x, for example, or even given the classes, within the classes, you are computing the probability of x given within the class, that is likelihood. So what would be your, what are the parameters you are going to estimate here in that case? Which are the parameters for multivariate normal distribution are to be estimated?
So mu and sigma.
How many? How many of them are there? Suppose you have d-dimensional space. You have d-dimensional space. So how many parameter you are going to let me see. You have a d-dimensional space. So how many parameters, individual components of elements of a vector or independent elements of a vector of or a matrix? How many of them are there? So how many in mu?
D.
Pardon?
So D.
D, right? Because there are d no attributes or d dimensions. So for each random variable, you need its mean, and it is exactly the sample mean of that particular column. That is the in the data matrix. If you take the mean of the columns, that is the estimation of mu, particular mu of that particular attribute. And so there are d. And how many of this sigma? How many parameters there? You need to compute.
So D into D plus 1 by 2.
Right. D into d plus, because you are going to find out the pair of combinations, and since it's symmetric, it is d into d plus 1 by 2. So there are so many parameters that you need to compute using the same method, maximum likelihood estimate based method, or the Bayesian approach. So I will just give you the results now with this. So once again, you see that you are estimating the class likelihoods through parameters, and once you have estimated the mu and sigma in the same way, you just extend the method. As such, these are the mathematical notations, algebraic notations, but the computation is simple extension, because there you are computing sample mean of individual attributes in the individual dimensions. Whatever data you get, you compute the mean. So that would give you the elements of mu. And similarly, you compute the individual variances and covariances. Sorry, any given any two columns, I mean any two random variables there, that would give you the estimation of the covariance matrix. Again, the biased and unbiased, both that no correction, that means correction for making it unbiased still remains valid there also in the same way. So that means you have to divide it by, if there are n instances, if there are n number of rows, you have to divide it by n minus 1. So, but no, individually you can, independently you can compute them and you can form these matrices. That is your estimated parameter mu I and sigma I given a class. So within the class, you are restricting the instances within the class and you are computing all of them. So once you have that, now you can see that your discriminant function looks like this, isn't it? So this is your discriminant functions, because I have taken the log likelihood of these distributions. That means log of Px given Ci plus log of Pci, right? So this is the log of likelihood, because denominator I'm ignoring. Denominator part I'm ignoring for the Bayesian inference. That is the marginal probability of the data, which I'm ignoring, because it is same for all classes. So these two components are there. This is from the prior, and this is from the likelihood. Now you can see that this part is once again constant. So what it remains this part only. And again, it's a quadratic function. It's a quadratic classifier in that sense. But you can simplify once again to linear if you have certain assumptions. One assumption is that let this sigma I becomes same for all classes, which means this also goes, right? This is same for every class. So if it is now, this becomes only represented by only the same covariance matrix. So you have, of course, mu i's are all class dependent. So I should have this index mu I. No, that is missing here. So it should be mu I. So which means it is now this becomes this. And if you can simplify it, you can show that actually it becomes linear. So certain simplifications are also here. I would like to show. As I just mentioned, the parameters by computing mean vector and covariance matrix. So the discriminant function is quadratic here. And if the covariance matrices are the same as I was mentioning, the discriminant becomes linear, right? And if all the features of X are independent, then what happens? Actually, your covariance matrix becomes diagonal. That means all covariance of two different random variables, they become 0 if they're independent, right? Because you can prove that, no? Expectation of their product is the same as product of their expectations. So your covariance becomes 0. So in that case, you are having only diagonal elements to estimate. And then you can also see that your classifier simply looks like this, because no, you are not having all those, you can reduce these classifications in this fashion. Once again, it becomes a nearest neighbor classifications if even all covariance is sigma, basically sigma ij, actually it is sigma j square. It is sigma j. It should be written sigma jj, right? Covariance diagonals, only the diagonals are written. So if you're I have not shown those simplifications. It becomes linear when they have all same variances. That is one thing. Any questions till that? Do you have any question? Okay, so let me proceed further. Now, let us consider the discrete features. So, see, Gaussian distributions, these are considering the random variable in the real space, which is a continuous variable in the continuous space. But no, if I consider a variable with discrete set of outcomes, like the Bernoulli distributions we have discussed, Bernoulli distribution for a single random variable. But let us consider you have multidimensional random variable and each following certain Bernoulli distribution. So we'll be considering something like that. So that is what you have d-dimensional random variable, and each dimension of this variable representing an attribute, a random variable which follows a Bernoulli, which means its outcome, there are two outcomes, 0 and 1. and they have a probability of outcome. One of them, probability of having the value 1, say, let us consider that is for the jth one, that will be pj, otherwise it will be 1 minus pj. So let us consider this, that probability of xj equals 1 given a ci is pij. So given a class, how many parameters are there? If I is fixed, how many parameters are there in this distribution that you need to compute? Have you understood my question? Anyone else?
So D.
It would be D, right? It would be D
Yes.
for a given a class. And if there are, say, k classes, so it would be k into D, as you see, right? That would be the case. Now, this is, once again, now extends the mathematical representation may look little clumsy to you, but they're simple actually. But since it is multidimensional representation, may look little yeah, complex. But computationally, they are very simple because that's simple extension of your results of the single dimensional variable. So in this case also, for each attribute, independently you find your estimation was fraction of times that random variable, that outcome is 1 in a particular dimension for a particular class. So you simply find out that, and that would be the estimation. So in fact, no, you can write the class likelihood in this fashion, and then the discriminant functions would be this, and it could be a linear functions also. So estimation of that estimation of Pij, that means given Ci class estimation of the probability of having xj equals 1, it is simply the number of times xj is 1 in that class, given the total number of occurrences of xj, including 1 and 0. So that is what is Pij. So if you get the Pij, then no, you can get these discriminant functions for this class itself. And also prior probability, no, you need to compute in the same conventional way. So you can see it's a linear function once again. It's a linear functions because you can see that log Pij is and log 1 minus Pij, they are the coefficients, actually coefficients of the variable xj only. So it's a linear functions over the attribute space. So some application, if I say about these discrete random variable cases with the parametric estimation, say you can consider certain characterization of the document. Suppose we want to see whether a document is a news item or not. So what we can see, we can do, for example, you represent each document by a vector of bag of words. So each word is a dimension, and it could be, that in natural language processing, this is a very, or information retrieval, I should say, not natural language processing, information retrieval. This is a very common technique, particularly when you are characterizing a document, that whatever words are there in the document, there is a particular corpus, what is being carefully built up, given, and you find out for each word in that corpus is a dimension, and your observation is that no, in various ways you can represent them. One simple representation is that how many times that word has occurred. One simple, but there are various ways you can represent it. Anyway, so as I was mentioning, represent each document by a vector of bag of words, and there it's a Bernoulli outcome, as I mentioned, that no, for each word, how many times, what is the probability that that word will occur. So xj denotes whether jth word in the bag of words occurs or not. So estimate Pij from the training data set, obtain discriminant functions for each class of documents, and then you can use them. You can use them. Once you have an instance. So there you can simply compute this function and find out which one is giving the maximum. Now this also can be generalized for multinomial cases. Multinomial in the sense I have considered Bernoulli random variable for each attribute. Instead of that, I extend it for k outcomes. Instead of 2 outcomes, I can extend it in k outcomes, and in the same way what we discussed earlier also, we use a dummy indicator variable there. Indicator variable in this case is z, j, k. And so you have rather parameters also for each, each outcomes, based on each outcome. So you have another dimension added to that. So this representation is the same, simple extension, and you can show that this is also a kind of same the linear functions, what you get. So with this, let me summarize the parametric methods that we have discussed, parametric methods of Bayesian classification. So first thing, as we have seen that we have estimated the parameters by using likelihoods and either using the maximum likelihood based approach or using the Bayesian inference posterior based approach. Then discriminant functions are obtained from the analytical forms of the posterior. Also, we can consider that mean and standard deviation of classes in feature space from the parameters of normal distributions. This is something we discussed. So, yeah, I mean, normal distribution. What are the basically estimations? That's what it's mentioning. Probabilities of occurrence of Bernoulli features from the parameters. And the same analysis could be extended for multivariate class distribution. Okay, so before we proceed to this other method of Bayesian inference, which is a non-parametric approach, let me announce one thing that we will have your second quiz. That would be on week after next week, next Thursday. That means 7th October. Okay, so you will have the second quiz there in the same way what has been conducted in the first quiz. And the syllabus would be that next week till Friday, whatever I cover, that would be the syllabus of your second quiz. So let me again come to this part that we'll discuss about the non-parametric approaches for Bayesian classifications. So here we see that the flavor is that we are not estimating any density functions using parameters. Rather, we are trying to give a representation of a density functions. So it is not a very simple algebraic form in that sense, but it could be also expressed in a composite algebraic form or locally defined functional form. So I will come to that. But one of the assumptions in non-parametric approach is that we observe the input patterns and we consider that similar inputs, they have similar outputs. So from there, we try to predict or try to classify the things that by looking at the input distributions in the data distribution in input space itself, given an unknown input, we try to categorize that how similar it is with some of the labeled input and try to get a level of that unknown input based on that. So one of the characteristics here also is that there is no assumption on form of density functions. We are not assuming that they are normal, etc., etc. And that's why it is not parametric method also. And we are estimating the probability density locally. I mentioned that that means the representation of your density function as if it is a piecewise definitions of some local functions. It may be continuous, it may be not continuous, may not be continuous. Whereas in the parametric approach, we estimate the density functions using all samples together. So, vis-a-vis these non-parametric approaches, your estimation of a probability given an unknown sample may be done locally. So you need not consider the effect of all samples. So you are trying to get more information, you are trying to give more weightage to the information related to the similar inputs. That is the kind of level. We call it also instance-based or memory-based learning because you will see that when you discuss about the techniques, you can understand its meaning, particularly that actually since you are comparing with the inputs, so instances, so you require to remember those instances or store that instances and and compare as and when required the instances which are nearby. So that's what you need to store samples in memory for lookup. But that's why it is very computation intensive, because no, if you are having n data point, so you see that no, you require a memory space of at least linear memory space at least, and also in the computations also sometimes it may be also linear. So, but no, when you have a parametric approach, actually you can see that once the parameters are obtained, then the computation becomes simpler. Like estimation of parameter is one-time job. There, of course, no, you have to handle all data, etc. But once the parameters are obtained, you ignore the data. You ignore the data point. You just work with the parameters. So that's why the number of parameters will decide. That means the number of parameters are basically the dimension. So either uh, linear or a function of that dimension. So that is how. So usually D is very less. Number of parameters is very less compared to the number of input. I mean, that is, you not only usually it's most in every cases you will find. Otherwise, no, your number of sample, if it is too less, it is meaningless to do this kind of approaches. So N is very high compared to D, and that's why parametric approach is efficient in that way, storage wise, and also even, I mean, I'm talking about the computational classifications, right? So that decision making, inference mechanism. So that computation requires less storage and also fast. So we call this learning is lazy learning compared to comparing the parametric approaches. So the first technique that we will be discussing here, let us again restrict ourselves to univariate case. That means with a single random variable. And they are once again the same way the data set is represented. As you see, there are n instances. You are considering that. So what we can consider that how do you compute the, for example, probability of x lying within certain interval? It's very straightforward. Empirically, you can compute. So you simply compute the cumulative probability, and from there you can always get the probability density function. That means you compute that till what value. Um, so I will just explain with respect to mathematical form. So you see that if I say cumulative probability, that definition is that uh, for a value x, uh, whatever the sample value less than x number of times, so fraction of times it occurred, that is the cumulative probability. So when we say the density, it should be the within certain interval, what is the number it is occurring. So you see that interval is h here, and then you consider that the probability within that interval, and since it is density, then you divide it by the width of the interval. So that is h, right? So this is a density. This is the probability density function. So you can see that this is non-parametric way of estimating the density functions for univariate case. So the naive estimator would be that you compute these density functions. So you can use the histogram of bin width h, and it's like you can consider instead of uh, x plus h and x, you centering around x, you consider the interval from x minus h by 2 to x plus h by 2, and you can do that. You can use the histogram of bin width h, and the same way you can, you are doing it. So once it is computed, now you can see that your training samples are not required to estimate PS. So now if I give you any x, you can simply look up this table and you can find out what is your probability of x, because you know that the density functions, and you can, using this lookup table, you can always do some mathematical integrations over that interval, and you can compute the density functions. So so this is what is very empirical way of defining the probability density functions from the data. There is another interesting method, and which is very interesting from the functional analysis point of view. You can also have an algebraic representation. As I was mentioning that instead of representing the probability density function as a global function over the space by a single algebraic form. What we can do that we can consider it's a piecewise continuous function, right? Piecewise continuous function, and you are defining over certain interval. So this continuous function is defined with respect to the data point locally, and aggregation of all of them will give you the total probability density functions. So this is when we define locally a continuous function representing the probability density due to that sample at that point, and at that point, so that is called kernel. So you can see that actually kernel is a function of distance used to determine the weight of each example. So that is the meaning of kernel, and it can be used for representing also that since already this sample has observed, so we give a higher weight for occurrence of a sample at that point, and around that weight decreases as as it is getting more distant from that sample with some functional form. So we can write the kernel as a function of distance from that sample xt in this way. So there is a kernel estimator, and which is also called Pearson window. So this estimation can be considered in this fashion. That means you define a kernel around xt, and suppose there is a weight h. So what we do that you consider that this representation gives you the probability of that interval around that sample xt, and the interval width is h, for example. So outside that box, that means it's like interval. So outside that box, we are considering univariate cases. So let us consider, say, xt minus h by 2 to h by 2. That means interval is h around xt. So that is the definition of the kernel. So because you can do it for the as a function of distance, so it should be symmetric around xt. So if I consider the overall integrations over that is 1. So what is the total for all the data points? The total so you should consider 1 by h also. So the total number of width is nh. So finally, you get the density function in this form. So some of the kernel definition. One definition is this. That means you have uniform distribution locally of a kernel around U. It is half and half. You can see that actually x minus xt is represented, x minus xt by h is represented by U in this case. So it is taking care of scale. It is taking care of also the translation. So both translation and dilation both are taken care of. So we can represent it, or you can have a smooth integrations. You can see that it's a Gaussian functions, and if you integrate it over the space, so here actually your function is defined, kernel is defined over the whole interval of real interval, because Gaussian function, as you know, it is defined over the whole interval. So weight, though there is a standard deviation, some kind of effective weight, but it is defined over whole interval. So accordingly, the kernel has to be, the probability density function has to be adjusted. So with this, let me then, with this background, let me explain what is meant by k-nearest neighbor estimator. So k-nearest neighbor estimator, in a simple term, let me tell you algorithmic interpretation first, and then we will give you some analytical explanation. So algorithm-wise, it is very simple. What you do that you find out, given a data, given an unknown sample point, you find out the instances which are within its k nearest neighbors. That means you find out the nearest neighbor, then second nearest neighbor, then third nearest neighbor, like kth nearest neighbor. You compute them, and then now within that sample instances, you consider the occurrences of a class. How many times a class has occurred? So you consider the levels and find out fraction of times each class has occurred. So each fraction is indicating a probability of occurrence of class. That will give you the posterior probability. So probability of occurrence of the data X, that is unknown sample, given the class. That is a close estimate of the posterior probability. Analytically, we can show. So now it becomes like Bayesian. So whichever is maximum, you assign that class. Is it clear? Any question? I have not gone through the details, but this implementation algorithmically, is it clear what you are really need to do? Okay. I can ask someone. Alok Dhiman, are you there? Seems Alok Dhiman is not there. Orijit?
Yes, sir.
Yeah, Orijit. So Orijit, can you tell me that what exactly what computation K nearest neighbor estimation for class assignment we are doing? Just summarize. Can you summarize it? What I told?
Sir, first we determine the k nearest neighbor to an instance, and then we compute the probability of the data given a class Ci, and the class that gives us,
How do you compute that? How do you compute that?
sorry, count the number of classes in that k instances, and divided by the total number of instances for each class.
Divided by K. Divided by K.
Divided by k, yes, total number
Divided
will
by
be
K.
k since we consider k nearest
Right.
neighbors.
Right. Right.
And the class that will give us the highest probability, will assign that class to that.
Very good. Very good. You are right. Okay. So let me continue. Right. So now I will give you a little more analytical explanation of this technique or representation of this technique, and you will find exactly the computations what Orijit has described that we will be doing here. So as you see that distance in this case, so you are defining a kernel. I told that it's a function of a distance. So when you consider an univariate function, basically distance is defined in this way. That means given 2 points A and B, distance is simply their differences in that axis. So we consider the distance of the ith nearest neighbor from X. We represent it in this way, that dix is the distance of the ith nearest neighbor from. That's the functional representation. So if I consider the kth nearest neighbor, so the width of that distance, like that defines effectively the local width on which you are computing this probability density posterior probability density functions. So this is one thing. That means if the distance is dkx, which means you are taking the effect over twice dkx entering that sample x. So you are doing k nearest neighbor density estimations by considering. So if I consider the data, what is occurring over, so how many, because we have taken already the k samples, so we consider k by n, that is the probability of data in that interval, right? And then adaptive kernel estimator. So no, you can use the kernel value instead of that is an empirical way of estimation. But if you use the kernel estimation, you can consider this is a kernel estimate. You can see that instead of h, I am writing it twice into dkx. Rest of the things remain same. So this is a probability estimation. So multivariate density estimation means when you have multidimensional space, instead of h, you consider that volume of h to the power d instead of simple width, but rest remains same, and you always consider your integration of kernel is 1, like the Gaussian I said, that like Gaussian kernel looks like this, right? And you can use also covariance matrix. You can use for discrete case like this. So this is how the k nearest neighbor is, example non-parametric classification. These are the labels, as you see, it is given, and you are computing the probability of a class is ni by n, that is overall distributions, and given a sample, you find out the locally what is the probability, posterior probability, and which is given by this. The KNN estimator is given by this, right? So you find that posterior probability becomes actually that ki by k. which is what you are actually computing. I told you fraction of times the samples of that class has occurred given the k instances. So that is what is your posterior probability, and you are assigning the classes there, right? So maybe just let me summarize this part and then I will stop. So you can see that this is a very simple example, but this is also a very powerful classifier, though it has many disadvantages as well. It is simple, that is the best advantage, but it has many disadvantages. And we call it instance-based learning because we are storing these instances, and as you can see that there is no training. As such, there is no computations for training. That is the simple thing. You only do the query processing. After storing, you find out how many of similar instances are there, and then you classify. You can also use them for regression also. So significant advantage over complex target function is that instead of computing a global function, you are computing it locally. I have talked about k nearest neighbor. In the next class, I will discuss about locally weighted regression. The learning is lazy, but delayed until a new instance gets classified, and instead of computing once for all, you are computing it incrementally, right? So today, let me stop here. And as I mentioned that your next quiz would be on, I think the date is 7th October. That is on Thursday, again in the same class hour, 12 noon. If you have any questions, let me know. I will just am downloading your attendance. Okay, so it seems there is no question. Okay, so thank you very much. So tomorrow morning, once again, we'll discuss. We'll have the next class.
Thank you, sir.